afternoon, everyone. I want you all to have a look at this dress. Please study the different attributes and think about your own opinions about these attributes as well. Some of you might focus on the color of this dress or what material it's made of. Some of you might think that you want to use this on a Friday night, but the person next to you rather want to use it on the beach during next vacation. What we do know is that we're not focusing on the same attributes, and we're not thinking the same about them either. From an organization point of view, understanding this correlation between the product and the customer and turning that knowledge and insight into data is a key component when utilizing machine learning within organizations. And the more complex the product that your organization is dealing with, the more important this task becomes. My name is Jonas Grunditz, and I'm working on this task on a daily basis with my colleagues. How we can understand more and deeper things about our customers and our products. And I'm very excited to be here representing the H&M Group on the machine learning stage. Normally, organizations are structuring their data in a tabular data format, where the columns are representing different features. For example, of this dress, it will be the color or the material. This is a good and cheap structure to structure data, especially when it comes to easy estimation things. But when you're trying to work with more complex things, estimating more complex tasks, such as establishing computer vision systems into the real world, or working with understanding fashion or music or recommending movies, then your tabular data might fall short. I was in a meeting a couple of years ago when we were discussing exactly this. How can we understand our products and customer better by enriching our tabular data? And there was one person in this meeting expressing that we should outsource this to an external provider who is labeling this data for us. This means that a group of people would individually go through each article and label the data that they are seeing, just like you did before. So depending on their knowledge and their opinion, they would have an effect on our data and how we utilize that into machine learning models. So ending this meeting, in the end of it, we turned out to use something else, embeddings. This embedding space is reduced to 3 dimensions for visuality, and you can see some correlation between the articles when it comes to color. And if you actually zoom into this embedding space, you can see that they look quite similar. When creating these embedding spaces, you really need to focus on the core product that you're working with within your organization. At H&M, it's fashion. So we need to break down fashion into components which we want to measure correlation for. And when it comes to H&M and our customer domain, our recommendations systems is of importance, and therefore we need to break that down. And things that we need to take in considerations is, for example, when a customer is looking at our products, what are they focusing on? What do they like? And we need to capture that using computer vision and image data. We also want to capture things such as when a customer is touching the material of a product, how does that make them feel? How does that material is different from other products' material? Other things that we want to capture is when our products are being used, what style do our products have, and what our preferences of our customers. There are basically 3 different areas we have defined for creating these embedding spaces. First, you need to choose the encoders. Then you also need to focus on the business applications within your domain. Then you also need to select a data set to optimize this on so that you're reaching your business goals. But also picking a model architecture and a loss function for actually creating these embeddings. Starting with the encoders, I've been talking a lot about embeddings and encoders, right? So what do we actually mean by encoders? At H&M, we are saying that encoders is a way for transforming data into a usable data source or shape that we can use as inputs into our other models. An example of this is one-hot encoding, one of the simplest versions. If we want to one-hot encode this sentence, "We love fashion and data," it will look something like that. A one-dimensional vector where it's a binary representation where you have a 1 if it's represented in the sentence, and if it's not represented in the sentence, it will be a 0. And the problem with this is that the more words that you are working with, the more sparse this vector is going to get. And the correlation between the words are not considered. So by starting, if you want to understand this meaning, for example, on a deeper level, you can use embeddings. Embeddings in this case will take in consideration the position of different words, the correlation between them. Are they used after one another, and how are they used combined? Here you can see the encoders that we mainly focus on at H&M. Tabular data, text data, and image data. And in this particular example, you can see an example of an encoder of images. A simple convolutional neural network, starting off with a feature extraction part, followed by a classification part. And in the middle here, you can see the flathead layer, which is representing mostly our embedding spaces. So the reason why I'm showing you this slide is because you can tweak the embedding space and change how you create features depending on this classification task. In this case, we're trying to predict whether this dress consists of cotton, silk, or leather. But if you want to change this, you can adapt the embedding space to your domain by changing it to a regression task or just completely change the architecture of it, which I will show you a little bit later. Now I want to show you how we are identifying business applications, also selecting data sets and structures of our networks, and a loss function for actually creating these embeddings at H&M. This first example is when we give similar product recommendations. It's when a customer is going in on H&M.com or at any of our other sites, and they're looking at a product that they like. And here we want to stay relevant to our customers, and we want to increase the shopping experience. So we want to give recommendations of similar products. It can look something like this, where you see the dress in the middle, and here you see some recommendations. And in this case, we want to create an embedding space which captures similarity. And then a good question is, how do we define similarity? It's based on what our customers define as similar. What I mean by this is that when creating these embeddings, we are looking at generalized patterns of how customers are behaving on site. What are they clicking on? What are they end up buying? What are they adding to bag, to favorites? How much time do they spend on certain things? And we check on this on a generalized level and draw patterns from that. So in this embedding space, we want all of these dresses that are similar to be very close to one another. And another aspect of this is that we want to capture, for example, in this jacket, that they maybe not look very visually, but what they all have in common is that they're resistant to rain. So that is of importance when it comes to recommendations of this jacket, the similarity in the material. When structuring the embedding space, we start off with values that is pretty randomized, where the anchor article, which is the product that our customer is looking at, is very close to this similar looking product here. And it's very far away from the similar looking one. When we are training our model, we want similar products to be close to one another. And we create a unified embedding space where the distance is taking similarity in consideration. And the reason why we want this setup is because when we are giving recommendations on site, we can query the embedding space for the closest articles to the anchor image and recommend those. We are using a CMS network plus a contrastive loss function for creating these embeddings. The reason why this is a CMS network is because we're using the same encoder for processing the image data of all of these 3 images. So they're sharing the same weight, and we're updating the same weights during the back propagation. This encoder outputs a one-dimensional vector for each and every one of these images, which we are using the contrastive loss function to squeeze together the anchor image closer to similar looking one and push away the dissimilar looking one with the margin from the anchor. And the choice of the triplets here, the encoder, the distance function, and the margin, is totally up to you to decide, depending on your expertise and your domain. In this example, we're using an image encoder, but if you have other data sources that you want to utilize within your organization, you can add those as well. By keeping the same structure, but just adding those, and all of them with output a one-dimensional vector each, which we can aggregate to a longer one-dimensional vector and use in the same calculations. So in our first example, we identified a business case. We want to give similar product recommendations. We selected our customer behavior dataset for optimizing this, a CMS network plus a contrastive loss function for actually creating these embeddings. In the second example, we want to give outfit recommendations of things that goes well together. And we have the same situation. Our customer is looking at a product that they like. And we want to stay relevant to our customers, so we want to give recommendations of something that goes well with that product. So if they're looking at a pair of jeans, we want to give a recommendation of a t-shirt maybe that goes well. In the previous example, we created an embedding space where similarity was important. In this case, we want to create an embedding space where similar things are close to one another. Here you can see an example of the recommendations where you see a white shirt in the middle here, and we give some recommendations, for example, this belt or jacket or shoes, for an example. The data we're using here is images of our articles. We're using the textual descriptions of the same article as well, and some style compatibility connections. And that is just basically our domain experts telling us what articles goes well together or not. Now we're using a graph neural network instead of the CMS network. And we're also using a binary cross-entropy loss function for creating this. And usually when we start creating graphs, we want to actually construct the graph from the beginning. So what I'm usually picturing myself is a completely white page where we want to pick out the different articles and put them on this white piece of paper so we have the structure of the graph. And we get the structure from the edge properties. And the edge properties is based on some generalized transactions, but also our domain expert dataset. And you can see here, in this example here, that if two things goes well together, they have a white binary line between them. And if they don't go well together, they don't have this binary white line. Now we have constructed the graph, but we also need some more information about each and every of this article. So what we need to do is to create a one-dimensional vector with these encoded versions. So we encode our image data, our text data, and some tabular data. And in the example here, we're using a pre-trained ResNet model for encoding the images, a pre-trained BERT model for encoding the text, and some just transformation of the tabular data. And all of these are outputting a one-dimensional vector again, which we aggregate together. So the graph structure is made from the edge properties, and the information comes from the node properties. The reason why we want to create a graph from the first place is to predict whether two things goes well together. And from our domain expert dataset, we know that this pair of black jeans, for example, goes well with these shoes and this shirt. But the question is, does it go well with this randomly picked red jacket? And we're asking that question, filling in that in our assortment graph to get the link predictions. We are training this model, this graph neural network, with the inputs of two items that we want to check if they go well together or not. And it outputs a binary yes or no if they does. And the input values here are the node properties, the information encoded versions of our images, text, and tabular data, and the neighborhood of these node properties. So we're using that for both the jeans and the shirt in this example, And in the middle here, we have just a bunch of feed-forward layers trying to get the correlation between what goes well with each other or not. And when we have trained this model, we can query the embedding space, like we did in the previous case, looking at what are close to one another in it, and recommend those. But we can also use this embedding space as input features to a second model right afterwards. So in this case instead, we identify the business case. We want to give recommendations of things that goes well together. We selected some data, and we picked the graph neural network plus a binary cross-entropy loss function for creating these actual embeddings. I hope I have inspired you a little bit to go into your own organization, check what kind of business cases you might have that can be approved by using embeddings and numerical representations instead of only using your tabular data. But if it's one thing that I want to take with you, that is, if you're seeing that your input features in your current models is not enough, you need more data about your products or your customers or anything else, then numerical representations can be a good way forward. If you have any questions about this presentation or you just want to have a general chat with me, go to booth 61, which is the H&M Group's booth. And thank you very much for listening. And otherwise, I see you in the crowd.